postdoctoral research.
Postdoctoral research associate at Series, right?
Series, yeah.
At Series, okay. And he's going to be talking to you today about more ice and slabs and things like crevasses and stuff like that. So, take it.
So yeah, hi, my name is Mike. I am one of, I guess, numerous glaciologists you'll have been hearing from in the last couple of days here. Most of the work I do is in Greenland, and most of it is dealing with stuff on the surface, snow and ice and melt and runoff, and things that are occurring on the surface of the ice sheet in Greenland, which it turns out are having some really, really big effects on the whole ice sheet right now. And really what I'm giving you is an overview of some of the current science that's coming out that's happening in Greenland, certainly not all of it. But most of what I do isn't dealing with old like ice core records going back thousands and thousands of years. We take ice cores, I'll talk about that in a minute, but most of what I do is dealing with the very recent stuff, past 50 years. A lot of major changes happening right now. So I'm going to start first story. I've got three different papers, three different projects actually I'm going to go over in 30 minutes. And most of what I deal with, as I said before, I need to put a couple of terms out there that most people aren't familiar with. As snow on a glacier builds up year after year after year, it slowly compresses into glacial ice. And in the middle of that, after it's a year or two old, between 1 and say a couple hundred years old before it's completely squashed down into ice, it gets this intermediate state we call firn. It's kind of like cinder block. And so whenever you hear me say firn, that's what I'm talking about. Just think really old crusty snow. If you think of snow that's been sitting in your driveway and it's been there for 50 years, how old and crusty that would be, it's kind of the consistency we're talking about. And water, in areas where there's some melt on the surface, will trickle down and refreeze into these little layers of ice that are in the firn layer. About 7 years ago now, it's hard to believe it was that long now, I was with a Danish team out in the middle of the ice sheet in southwest Greenland in an area called Canyu. And Canyu, it's an area that receives some melt every year, but we were there studying sort of what was happening just under the surface because this area had received a lot more melt in recent years than it had previously. This was spring 2012. I was there with a firn core drill. 2010 had been a record-setting melt year there. 2007 had been a record-setting melt year before that. 2002 had been a record-setting melt year before that. So we were there to sort of, among other things, see sort of what was going on in the firn underneath our feet. And again, what we were sort of expecting to find is firn interspersed with these various ice layers. You see more ice layers up toward the top than there are further deep, because the deeper down you go, the older it is, and there's been a lot more melt recently. What we ended up finding was core after core after core of just solid ice. After we got down to the surface, we pulled up nearly, this is one of our ice core records, the blue spans of the solid ice. We drilled right through under the surface, about 5 meters, about 15 feet of solid ice right under our surface before we started to get into a mix of ice and firn again. There's a whole lot of ice right under our feet. And we were sitting in camp one ridiculously warm afternoon waiting for our plane to pick us up. And wondering, well, this is a lot of ice right under our feet. We had drilled several cores in different spots and we'd taken some radar data, and we could see anywhere you could look, there was all this really thick layer of ice sitting right under the surface. And we were wondering, well, so they had a lot of big melt years here. It's obviously causing all this ice that's refrozen under the surface, but how many more big summers could it take before the water's just got nowhere else to go? Because when the water's in firn, it can percolate down and trickle in and refreeze and stay put. But if it's hitting solid ice, like there's not a lot else for it to go. There's still a little bit of pore space at the top of the firn column above those ice lenses, but we were wondering, like, how much longer would it take? How many more of these big 2010 like melt summers would it take before you just started seeing runoff from here? So it had never run off from this part of the ice sheet before. We ended up getting an answer pretty quick. This was May 2012 when we were sitting here. In July 2012, Greenland had a record-breaking melt season. At 2 times during the summer, melt reached all the way to Summit Camp of Greenland, which happens once every few hundred years. Actually happened again this past spring, not that long ago. But it did it twice that summer, and it was just an incredible amount of the ice sheet. This is from satellite records, from passive microwave signals. They can detect what parts of the ice sheet are melting and what aren't. And this was something that hadn't happened in the recent observational record. It was an incredible melt year, but even more so than the little bit of melt that was happening on the summit camp was what was happening in our areas down here in southwest Greenland. And the news covered this stuff when it came out in 2012. It was also a year of record low Arctic sea ice extent. Sources covered it differently. National Geographic called it shocking. ABC News talking about scientists say they've never seen anything like it before. Fox News covered it slightly differently.
They have the same picture.
Who I said? Yeah, they had the same picture. Gotta give it that. Yeah, slightly different interpretation. This was the Watson River. Is the Watson River? It flows through the town of Kangerlussuaq in southwest Greenland. This is actually us sitting there in May at fairly low water flow. Almost this entire river, it does feed off the ice sheet. It actually feeds from the same glacier where we were up on the ice that spring drilling those cores. And this typically gets pretty low flow in the winter because it's almost entirely fed by the ice sheet. It gets higher flow in the summer. This canyon fills all the way up. The U.S. Army actually built this bridge over it in the 50s, and it's been there since 60s, I think. This was that bridge in May. As things were melting all the way up to summit camp, an incredible melt was happening all over the ice sheet. This was the same bridge in July that year. Oh. That's a caterpillar river being washed right off the bridge. Nobody was in it. Right. They'd never seen runoff that high in Greenland before. It had never touched the bridge before. It actually washed out a couple of parts of the bridge. It took them Greenland and Denmark 6 million Danish kroner, nearly $1 million to rebuild and re-pour abutments on that bridge. And unlike, say, that, I don't know how many of you are locally here or not, but in Boulder they had a big flood in 2013, and it was due to like 5 solid days of rain. This wasn't like that. This wasn't just a brief rainstorm or a brief melt event. It was most of July it was blowing like that. It was a tremendous amount, broke all kinds of records in Greenland. And as I was looking through satellite records later that summer, came across this image from the 16th of July, mid-July, of that summer showing slush fields. Ignore the strikes, that's just a satellite effect. But slush fields forming around the area where we were drilling, right there. And then, sure enough, slush fields forming on the surface, channeling off into rivers, going off down slope, helping wash a tractor off the bridge in Kanger. And we had our answer about how many more melt years would it take before water would just start pooling at the surface and running off, rather than just staying put and percolating down and refreezing. Took one more big melt summer. And it turned, I mean, that was very, in this respect, it was very fortuitous that we were there. This particular area, I'd set some instruments there that I buried under the surface that got completely melted out and destroyed. So my instrument was a complete failure that year, but we didn't get those cores, and we knew we had a story to tell. There was something going on here, and we had some data, but we didn't have a lot of data. What we had was cores, a few cores at one particular spot. We could tell there were these layers of ice a few meters thick. Well, we didn't know these layers of ice near the surface, how far they extended, how thick they were at different parts. We didn't have a lot of data. So what we did is we scrounged together through a lot of pushing and more than a little luck to get a field campaign the following spring. Yeah. And actually, I could describe a bit visually here what was going on. Cut away at the ice sheet. Up high in the middle of the ice sheet, you got what they call the dry snow zone. This is like summit camp. Snow builds up over the winter. It doesn't really get warm enough most summers to melt it away. It just slowly compresses down into glacial ice. Down near the margins of the ice sheet, it's warmer there, lower elevation. You get what we call the ablation area. Snow still builds up in the winter. And in the summer, it gets hot enough down at the margins to melt it completely all the way and wash and start running off. You get that beautiful blue ice. It's where you get most of the pretty pictures of crevassed areas in Greenland. Feeds the rivers, does that every year. But there's a vast region in the middle, actually the biggest zone in Greenland, called the percolation zone. This is where Kangu was. You get snow in the winter, it partially melts away in the summer. That melt trickles down and refreezes into these ice lenses scattered throughout the firn. When you start ramping up the amount of melt, you get more and more of these ice lenses scattered throughout the near surface of the firn, And if you keep that up enough years in a row, what happens is these things start freezing together. You start getting little ice lenses that turn into bigger ice lenses and turn into bigger, what we've started to call slabs, these meters thick kind of layers that extend for kilometers and kilometers. And once you've got those there, big and thick enough, then it doesn't matter how much pore space you've got underneath. You can actually just be running off right over the top of them. And this is a way to sort of rapidly expand the runoff zone of Greenland. If you can just fill up the top 5 or 8 meters, then you've got a thick enough layer where you can just run off over the top of it. And that's what we were finding. But again, we only had data at one spot. So we planned a campaign in 2013, following spring. Turned out to be ridiculously cold in 2013. We were landing in negative 40 temps, and it was not warm that year. But we planned various cores. We planned an entire ground-penetrating radar traverse. This is where we could send radar signals into the ice and it would bounce off layers, and we could map where layers were under the surface. And again, this is that satellite image. This is a part of our ground-penetrating radar transects. And with the transects, doing some post-processing, I could actually pick out these blue areas, or areas where it's ice, and then the other colors are various layers of fern in the column. And that we were just doing on the ground by snowmobile. And even though this line didn't go directly through Canyon, it went about 3 kilometers south, the reason we picked this line is because NASA was flying an airborne mission, which has numerous radars on it itself, called Operation Icebridge. And Operation Icebridge has several frequencies of radar, and it was flying over the exact same line that spring. And so, the radar is not as high a frequency, and it's not quite as high a resolution, but you can make out the really thick stuff here just as easily as you can down here. And I don't really care about the little details for the question we're looking at. It's the big, thick layers I'm worried about. That's what I want to map out. So we had planned this out. We had cores all along this transect. We had ground-penetrating radar both on the ground and in the air. And the great thing about the Icebridge radar is over the years, they have flown tens of thousands of kilometers all over Greenland. So using the same processing, once I tuned it into the ground truth that we had, I could map out across Greenland where these really thick layers of ice are forming from higher melt rates and refreezing rates around the margin of Greenland. And we've, again, called these ice slabs. There really wasn't a word for these before we were putting them together, and somebody was calling them multi-annual low permeability ice layers, and everybody was, anyway, call them ice slabs. And we mapped them out in pretty high detail about where you can see all the gray lines of the Icebridge flight lines where Icebridge has flown, the airborne radars, and then these blue areas are the areas where we can see where these thick layers are. Not so much down at the very edge. That's where it's always been solid ice and it melts out every year. It's really this area, this percolation zone in the middle, where you're seeing it expanding uphill. And so far they cover this area. If I just draw polygons around these areas, it's about 69,000 square kilometers. It's about the size of West Virginia. Usually in glaciology, we like to compare things to the size of states, like an iceberg the size of New Hampshire broke off Antarctica. We're past little tiny northeast states now. It's New Hampshire. West Virginia is not one of the small states. And we do know that they are blocking percolation. We've seen runoff over the top of them. We've seen lakes forming on the top of these things, sitting on top of these, even though there's lots of pore space underneath where the water could go. We see them there, and they help enhance runoff in warm years. In 2012, it added about an extra 11% to the runoff in that part of Greenland. It was still a record-breaking melt year, even if you didn't have this extra area running off. But that tractor probably would have stayed on the bridge if it wasn't for that added boost we had from these ice layers, from these ice slabs. Now, I wasn't completely happy just mapping out where they are right now. We have a number of computational tools we use, models primarily, that we can use to map out where these have formed and how much melt it took to form. We call these regional climate models. They are climate models. You can run them they're called regional because you can run it just over Greenland or just over Antarctica or other parts of the Earth. And used 4 versions of these models to map out pretty good. If you look at these 2 maps, this is where the observations show where these things are, and this is where we've modeled them showing up. They match pretty well. And this is using sort of past weather events up until, in this case, up until 2014, which is when we have this map of these ice slabs in Greenland. Part of the reasons we use the regional climate models not just so we could create a map that looks kind of like this one. That's not really the point. The point is that we can use these regional climate models to project forward. We can use, just like they do with global climate models, we can see, all right, well, we know how big of an effect these things are having, how big of an area they cover now, but how's that going to look in 2100 or 2050? And so, and before I get into how we look forward, I want to get into what we call different forward-looking pathways. What the IPCC, the Intergovernmental Panel on Climate Change, called Representative Concentration Pathways, RCPs. At the last IPCC report, they put out several future scenarios that global climate models use to project out into the future to get effects on ice sheets, on permafrost, on the oceans, on all sorts of physical systems they can model out. And these are what we call concentration pathways, the amount of greenhouse gases in the atmosphere from now up through 2100, from, in this case, well, 2000 up through 2100. And RCP 2.6 is if we made drastic cuts now and things leveled off and actually concentration started going down to 2100. We don't actually use that model that often anymore because we've already kind of blown past it. That was starting with extraordinary reductions in greenhouse gas emissions starting in 2010. Didn't happen. The two that we're looking at are RCP 8.5. This is the burn, baby, burn. Anything we can dig up, we'll keep burning as fast as we can get it out of the ground, which is kind of the trajectory we're on right now. And just keep that going through the end of the century. This is considered the business as usual scenario. RCP 4.5 is a more moderate emissions where it's not, we don't make quite as quick of cuts as you did in RCP 2.6, but you make cuts until you can zero things out by about 2050. These days, that's considered fairly optimistic. Maybe we could beat that globally. I'm saying we, the global we. But those are generally sort of two future scenarios that we might follow as humanity. So using RCP 4.5 out to the year 2100, again, these top maps were now as of 2014. These maps are out to 2100 using that scenario where we zeroed out emissions by 2050 and the concentration stayed level after that. And the area of these ice slabs, which is over here, is sort of keeps increasing through about 2050 and then levels off, because if you don't keep warming things up after that, they grow to a point where they are and then they just kind of stay there. But runoff over the top of them just sort of keeps going up because once you have the slabs there, it will keep running off over the top of them. The RCP 8.5 is a whole different beast. They just keep growing through the end of the century. And curiously, everything just stops at 2100. Time doesn't actually end at 2100. We just stop modeling at 2100 and ignore what's happening after that. There are longer term models that ice sheet modelers use. There was a recent paper out, they modeled out to the year 3000, various ice sheet scenarios for Greenland. Turns out we could lose all of Greenland by 3000 if we went this line. But this is kind of scary. This is what the runoff zone of Greenland is now when you've expanded it, more than doubles it. In fact, it's multiple times the current runoff zone of Greenland if you just kept going out to 2100. And these results actually were just like a week ago accepted for publication, so you're getting a bit of a preview. They'll be out in a couple of weeks. But this is basically mapping out the expansion of the runoff zone in Greenland. If you think about having floods, if every time you flooded, you made the flood basin above in the upper part of the river bigger and bigger and bigger each time, the flood's going to keep getting worse. And that's what's happening. We actually went in one of our field campaigns in Greenland, we went and talked to the municipal managers in the town of Kanger there about that bridge. They spent 6 million kroner to fix this bridge, but they left it the same height as it was before. We're like, well, there's not a lot they can do. It's a small town. They can't spend $500 million on a giant suspension bridge. It was already a lot of money as it was. They did make some improvements, but we're worried. Not just for a bridge in Greenland, in a town in Greenland, but this is adding another 70 millimeters, about 7 centimeters onto the global estimates of sea level rise than what was there before. on top of all the other contributions. This is not counting icebergs that calve off the ice sheet, or even the runoff that happens in areas where it always ran off. This is just added to all of that. But that's not the only thing water's doing on the surface of the ice sheet, is refreezing and causing more runoff. A big surprise to us, after we've been out there in 2012 and 2013 at this CanU area, is we got a high-resolution satellite image, a worldview image, of a particular, this is the CanU camper, we were drilling those cores, and this is actually just a higher resolution version of that satellite figure I showed before. Showing, this was in August now, it just had a snow dusting, so a lot of it was dusted over, but you can see all these runoff channels, much higher resolution, going off the ice sheet from around the area of CanU. But when we zoom in on this high resolution image, something that really surprised me, like up at this area just north of CanU, we saw all these little stripes in there. And I was like, what are those? At first I thought they were satellite artifacts, like some satellites have striping in the images, but that's not what these were. If I look at other areas, here in the slush field, you can see some of these little cracks that are water filled. These are little crevasses on the surface. This is an area where crevasses aren't supposed to be. You get down low where the fast ice moves, the ice will stretch and form all these cracks in these really beautiful crevasses. You don't want to walk around there, you can fall in them and die. Happens to climbers sometimes. But they're not supposed to be up this high in the ice sheet. We've been driving over these things for 2 years and never knew they were there. Until we saw them in a satellite image, which was a little worrying to us. And it's not just worrying from a safety standpoint. Turns out actually the cracks are very, very narrow. We couldn't have driven into one if we tried. But when we first saw them, it was kind of scary. But the cracks also affect glacial ice. There's a little cutaway figure from a paper of sort of the hydrologic system of an ice sheet. You get crevasses that can fill with water on the surface. You get lakes that fill with water. You get the areas where there's fern. This is where we were drilling up here. Usually you don't see the cracks up here, usually. And you certainly don't see them filling with water way up high. But what can happen, it doesn't just affect runoff. When a crack fills with water, what can happen is that it can start a process they call hydrofracture. So remember, water is heavier than ice. So when water is pooling on the surface, it is heavier than the ice underneath it. And when you fill a crack, a narrow crack with ice, the water, the hydraulic head of that water, the amount of pressure, water pressure at the bottom of that crack, is actually stronger than the pressure of the ice pushing against it. And so it will force that crack open a little bit more. And if you have enough water, say from a lake on top, it'll force it open a little bit further and a little bit further. It'll crack straight through 2 kilometers of ice to the bed. And when that happens, you form what we call these moulins, these tunnels down into the ice sheet, reaches the bed, and it ends up lubricating the bed. You can imagine if you took that glacier goo y'all just played with and wet down the slide before putting the goo on there, what would happen to the goo? It would slide faster. Not only be deforming, but it would also be sliding along the same channel. So when you've got areas, now there's areas of Greenland where water always reaches the bed every year. The hydraulic system at the base of the bed will shut down in the winter when the water's no longer flowing, but then once the spring and summer melt kick in, it'll speed up a little bit. And it happens every year, and it's perfectly natural, and the glacier speeds fluctuate accordingly. But way up high, you don't get water to the bed. But suddenly we're seeing both this surface lakes and these crevasses way up high, which is worrying. There was a paper out in 2015 because people from satellite imagery had already been mapping where lakes were forming higher and higher and higher on the ice sheet. And everybody's saying, well, this is a big fear. If we're getting lakes higher on the ice sheet, that's related to where those ice slabs are forming. If you're seeing lakes higher and higher, couldn't it be causing hydrofracture of the bed and such? And Kristen Pointer is a colleague of mine. She was at NASA Goddard at the time. She's a crevasse modeler. She models crevasses. This is what she does for a living, does the fracture mechanics and all of that of ice. And she basically put out a story that was just like, whoop, time out, everybody. Lakes can form higher and higher, but the ice is too slow way up high to really be forming cracks. Like, we don't expect, despite these surface strain rates, that's how much the ice is stretching. We found that the upper limit of where crevasses and therefore moulins are likely to form is about 1,600 meters elevation. Basically saying lakes can form higher than that, But if crevasses aren't going higher than that, you're not going to fracture the bed. Chill, everybody. Can't use it 1,860 meters. Something's going on. So we're still working on this right now. It's a story we're getting out. But what we did is we actually got a small grant here through the University of Colorado that we were already having a campaign up to the ice sheet. We're going to Candy, we're drilling some cores, setting some instruments, and we acquired 5 GPS stations. It is these high-resolution, millimeter precision GPS instruments that you can put out on the ice. Put 5 stations on the ice in the area where these little crevasses form. So we wanted to see how these things are behaving over here, because we weren't really sure what was causing them. And so putting some GPSs out there to see how they're moving and how they're opening or closing and such through a year might help us explain what's going on, why these things are there. We got the data back, and the line plot doesn't tell you a whole lot, except that the speeds fluctuate a little bit through the year. The ice there is moving at about 55 meters a year. Isn't terribly fast for glacial ice. You get areas way down in the ice streams where it's moving a couple kilometers a year. But it's moving. Part of the problem is that in 2009, it was moving at 51 meters a year. There was actually a paper out in 2014 that was all about how it had sped up to 53 meters a year by 2013. We're like, now it's 55 meters a year. It's still speeding up. We can't unequivocally say it's because water is reaching the bed yet. We don't have that evidence yet, but it's suggestive. And the strain, this is the amount that the ice is stretching per year, is about 0.1%. So only about 20% of the strain rate you need normally to cause crevasses, just from the stretching of ice. Normally in Greenland, the temperatures the ice are at, is that Greenland you need about 0.5%, about 0.5%, not 0.1%, to be forming crevasses. So we don't suspect these things are happening just from the overall stretching of ice. Even with a little bit of a speed up, it's not fast enough yet to really be forming these things. So it leaves us guessing with other sort of hypotheses. And what I had an undergrad, Beth, who actually took this high-resolution worldview image and hand-digitized where every crevasse was. There's over 500 of them in this picture. Took her a while. But this is actually the area where our GPS stations were. But this is really curious. These cracks aren't uniform everywhere through the picture. They really are happening. The colors refer to the slope. These are little 1 meter contour lines across the area. It's very shallow slope in this area. It's less than 1% slope anywhere. When you're standing at the surface, it looks flat everywhere. If you stare long enough, you can sort of tell there's a subtle depression over there and maybe a slight hill over there. What's happening is these things are really forming when it's going over a little hill. And then they're closing down when they go in a little depression, and then opening up when you go over a little hill, and closing down when you go through a little depression. It's actually why most of them are closed right where there's a lake there. Curiously, there's one little crack that goes right into the lake, which is a little worrying. But this topographic dependency, really where these cracks are forming, depends on what sort of undulations there are in the ice. What this leads us to believe it might actually have to do with these ice slabs that are there, these thick ice layers that are near the surface. Because normally you've got glacial ice and you've got this thick layer of snow and fern at the top. And the ice is flowing this way over slight undulations in the bedrock. Bedrock's 2 kilometers below, but it's hilly bedrock, and so the ice is flowing over it. And this snow is sort of pliable enough to where when it's going slowly over the snow, you don't see cracks forming everywhere. But if you stick a big, thick layer of ice at the top of the snow, think of a shell now on top of the snow and fern layer. As that's going over undulating terrain, that's more rigid. That can crack. We suspect these cracks aren't all that deep. We saw someone pull water just drains into them and then drains right back out somewhere else. It wasn't yet hydrofracturing into the bed. But if one hits a lake, hard to say it couldn't. So we've got more questions than we do answers on these right now. This, I've given a copy of my slides that actually doesn't have these slides in because this is pre-published stuff, but this is what we're working on right now. We suspect this may be a mechanism for having crevasse zones form way, way higher in Greenland than anybody previously thought. All due to meltwater, really. Meltwater freezing, causing these sorts of layers, which then can cause cracking and then can form all kinds of feedbacks. These are these feedbacks we look into around the ice sheet. And the big dragon question with guys, well, okay, I mean, their cracks are already forming higher than we thought they could. How high could they get? We don't suspect they go all the way up to the top of the ice sheet, no matter how much melt water we put in there, because the ice isn't really flowing at the top of the ice sheet. You need some sort of flow to be causing these layers to crack as they're going over terrain. We don't know yet. That's an open question. So we're looking into it right now. How am I doing on time? We got...
We actually have till 4, including some questions from them.
Okay.
They have really good questions.
I'm ahead of time. All right. The last thing I want to talk about, this was a paper we had a few years ago. This is dealing with meltwater in Greenland, and something most physical scientists don't think much about is this sort of human, and in this case political and military, component of our environment. Throughout the entire Cold War, the U.S. had a very strong presence in Greenland. Greenland is much closer to what was the USSR than most anywhere else in the United States, and including most of Europe. And so the U.S. put a lot of bases in Greenland. This is actually a military C-130 plane that was dropping us off on the ice sheet. They still maintain a runway. But back behind me, you see this building. It's a 6-story building with a big radar dome on top. That used to be an old radar base up on the ice sheet. They would actually monitor for aircraft or missiles coming over the poles up there on the ice sheet. They called this the Dye Station. It's an abandoned building. It was abandoned in 1988. But you can actually, it's been condemned, but somebody some time ago broke the lock off, and you can walk in there and walk around. It's a really creepy place to walk. It's an enormous building to start with. It's our team going under it. When you get in there, there's still flowers on the table, there's paint peeling off the walls, there's still eggs in the fridge. It was literally just picked up and abandoned one day in 1988, and everything's been left since. There's books on shelves, there's paint peeling off all the walls. It's a really creepy place to walk around inside. You're just going like, if anywhere was going to be haunted, this would be it. But Dye 2 was actually one of 4 radar stations they set across Greenland. They had 2 on the coasts and 2 in the interior around the Arctic Circle, and many across Canada. It was a whole line. But it wasn't actually the largest base they built in Greenland. The largest one was one called Camp Century, up in the northwest corner of the ice sheet. And Camp Century was different than the other bases. It wasn't just a building up on top of the ice. This was actually one they had built underneath the surface. What they did is they carved out huge trenches, 25, 30-foot deep trenches, put arch grooves over them, buried all the trenches, and then had tunnels. They put buildings in there, they put all sorts of facilities in there. And it was this large underground base, just underground, that you would have a hard time monitoring from the surface. And it had a particular purpose, and I'll go into that in a little bit. It had a number of purposes. They did a lot of good science at Camp Century. They actually drilled the first core to the bed of an ice sheet at Camp Century in 1963. The Camp Century core is still referenced to this day, climate records and things like that. But they were doing other things there too. And actually, I've got a little video here I want to show you that it's a part of a half-hour clip. I'm not going to play a half hour, but I clipped 3 minutes out of it. One of the more curious things about this base is that it was powered by a portable nuclear reactor. Takes a lot of money to be carting in diesel fuel to run huge generators to power a base that can man 250 people. So they actually used one of the Army's 6 portable nuclear reactors at the time and powered Camp Century for several years. And this little video goes into that a little bit. I find it equal parts appalling and very entertaining.
On the top of the world, below the surface of a giant ice cap, a city is buried.
Everybody hear that?
Today on the island of Greenland, as part of man's continuing efforts to master the secrets of survival in the Arctic, the United States Army has established an unprecedented nuclear-powered Arctic Research Center. Located in a wilderness of ice and snow, Camp Century is 150 miles from Thule, its nearest base of supply. This is an ideal Arctic laboratory. For more than 90% of Greenland is permanently frozen under a polar ice cap which covers all if necessary, under polar conditions. This is the story of Camp Century.
There's a bit of problem like that.
The next phase was to be the activation of the nuclear power plant. Wearing the white safety hat is Captain Jim Barnett, in charge of this operation, who will tell you about this critical phase.
This next part gets me.
We took every precaution in the book, and some that weren't there, to make sure this would work right the first time. When the entire system had been carefully tested, it was put into operation. We were then ready to begin loading the reactor core. One by one, the fuel elements were removed from the barrels in which they'd been shipped, carefully separated from one another. Each of these bars, containing approximately 500 grams of uranium-235, was then unwrapped, inspected, and wiped clean of any dust.
They're not doing that right anymore.
Crewmen wearing protective clothing began to load the fuel elements in the
Don't want any toe cancer. They're just a lucky strike coming out of their mouth.
Within the next few weeks, the final touches were put to Camp Century. Today, powered by its nuclear reactor, this unique installation is a completely modern community deep under the ice. This is a far cry from the primitive Jamesway huts of the work camp, where 3 showers serve 250 men. Here, there are showers for all, and facilities for every modern convenience. This is the story of Camp Century, of the Army engineers who carved out the underground city, of the many other men in the United States Army who made this project possible, and of man's never-ceasing quest for knowledge.
Yeah, so lots to say about that. Turned out they had Camp Century installed there for about 7 years. They built it in 1959. They put in the nuclear reactor a couple of years later. They abandoned the whole place in 1967. It was only running for less than 8 years. And when they left, as they did with all the rest of these bases, they left almost everything behind. The nuclear reactor they took with them, that was by far the most expensive part of the base, but everything else, sewage, fuel deposits, all the wastewater from the nuclear plant, they piped in a heated pipe a kilometer away and dumped in the snow. It's all still there. And it's just been there getting buried ever since. Now it turns out when they built this base, they built it under the premise. This was in the accumulation zone of the area. Remember that cutaway of the ice sheet? This is where it just gets buried year after year after year. Anything you left behind would be, and I quote, preserved for eternity. That was the language they used. It would just get buried, and if you dropped a golf ball at that spot in the ice sheet, it would slowly get buried, slowly float its way out to the coast, and sometime tens of thousands of years later, it's spit out on the edge of the coast. And at that point, it's an artifact. They weren't actually concerned about that kind of time scale. Whether they should have been or not is another question, but they weren't. And so they went under the premise that anything left behind was preserved for eternity. Most of the stuff, it was more expensive to cart it off the ice than it was just to abandon it, wash your hands, and walk away. So they left it all behind. Same as they did with that radar station up at Die 2. They left it all behind. But there were some curious things going on at Camp Century. Part of the story about it is very intriguing. They had a kilometer-long railroad trench. They actually had a railroad with a single car on it there. The railroad trench didn't connect to anything. It was actually a footpath to the rest of the base. It didn't go anywhere. It didn't carry anything. So you're wondering, why the hell would you put a railroad trench up in the middle of a tunnel in the ice sheet for no particular reason? It turns out this was testing. It was testing for a project which was top secret at the time called Project Iceworm. There was a general, I see a little cringing at the front. It's very apt. So it was some general's idea that you could possibly deploy nuclear weapons from the Greenland ice sheet. Their plan was to have up to 4,000 kilometers of train tunnels connecting up to 600 missile silos, all buried under the surface, and they could ferry up to 400 missiles between the silos back and forth, so that Russians, even if they decided to attack, would never know where the missiles were at any given spot. And Greenland, being very close to Moscow and other vicinities of northern Asia, it was a place to try that thing. Turns out that ice moves. So these tunnels would creep in under each other. It's actually people whose job it was at Camp Century to be shaving off the sides of the tunnels all the time and carting ice out so it wouldn't crush the buildings. And the ice moves differentially. So when you dig a straight tunnel, it doesn't necessarily stay straight. Some of the ice flows a little faster than some of the rest. So it actually turned out to be that once they had this tunnel there for a few years, they realized it was going to be technically infeasible to keep train tracks running 4,000 kilometers spread over a big spider web across the ice sheet. They ended up abandoning Project Iceworm, thankfully, and abandoning Camp Century not that long afterwards. And this has since been declassified, but it was all highly classified at the time. Denmark didn't know they were planning this there. Greenland didn't know they were planning this there. But there's still a lot of wastes buried there. We wrote a paper, came out a few years ago. This is actually the same radar I used to map out ice slabs. You can see the base buried. It's about 30 meters deep now. It's been buried year after year for the last 50 years. Talking about surface melt, we're talking about these surface melt creeping higher and higher inland and runoff. The red areas are areas where it runs off year after year. The blue areas are the accumulation zone where it's buried every year. Similar kind of story. This is as of today, or as of 2013 anyway, what it looks like in Greenland. In 2100, Camp Century is in the runoff zone. And at that point, you are washing away layers of snow year after year rather than adding layers of snow year after year. It's not going to take tens of thousands of years for this stuff to re-enter the environment. It'll happen much, much quicker. And so we had a paper out about that. It's a whole backstory behind it. But it ended up, Greenland was furious when the paper came out. Furious with Denmark. And he put a huge op-ed in the largest Danish newspaper demanding that they clean up, because it wasn't actually the only military site that was polluted that the U.S. had left behind, and they put together an agreement, a treaty that Denmark was going to be paying to help clean up some of this stuff. But that particular agreement didn't actually include Camp Century. But what they have done, Camp Century, keep in mind, is still buried pretty deep right now. They've set up a Camp Century monitoring program that one of my colleagues runs out of the Geological Survey of Denmark and Greenland. They visit the site, they've done extensive radar surveys to see where the debris fields are, where things are buried, and keep tabs on the climate there. When the stuff starts to melt out and get closer to the surface, then you have to talk about whose job it is to clean it up. But they monitor it right now. It's very rare for a scientific paper we put out to have immediate political impact like that, but in this case it did, and we're kind of thankful for that. I am out of time, I actually went over it, but that's it. And yeah, that's what's going on in Greenland right now.
Thanks.